into integral calculus. This session we will only cover about half of the, or more than half of the concepts you study in grade 12. Specifically, the basic integration rules, the Riemann sums, definite integrals, motion with integration, differential equations, and slope fields. First, the purpose of integral calculus is to solve problems that could not otherwise be solved, like areas under curves, like work done by a variable force, centroids of regions, lengths of arcs, surface area or volumes of solids of revolution, mass of a solid of variable density, and so on. We will focus on areas under curves and surface areas and volumes of solids of revolution. The basic integration rule is the anti-differentiation rule. Integration is the same as anti-differentiation. Okay, so when you have a question asks you to find the derivative of the integral of a function, because the differentiation undoes the integration, so what you get is f of x. So this is the basic of anti-differentiation. And these are the basic integration rules that you should all be familiar with. Differentiation rules that correspond to integration rules. Also the trigonometric and all the integration. These are the very basic rules, nothing more. So we will start with a couple of warm-up questions that should be relatively easy to solve for any high school student. So in this type of problem, we try to make it, we try to apply the power rule here. So this is what we're trying to do, rather than trying the log rule or any quotient. So we will distribute this denominator, root x, for the numerator. So we have 3 over root x dx plus, and we have 4. Then we have x power 3 over 2 over root x dx. So write in index form, so it will be 3x power negative half plus 4. This is x power half down there, x power half. So when you subtract, you get x power 1, 3 over 2 minus 1 over 2. So now when you integrate, you should get a constant for each integral, but as we know, constants will add to one constant at the end. So as we know for the power rule, we increase the power, negative half will become positive half because we add 1. Remember, we add 1. Then divide by this new power. Same thing we do for x power 1. So that's x squared over 2. Simplify and you get 3 over half, that's 6 root x plus 2 x squared plus an arbitrary constant. So this should be choice or option D. Okay, so the next basic question about integration is the integration of sec squared x. As we just seen in the rule, integration of sec squared is tan x, but we need the derivative of the angle to be out there. So x squared, its derivative is 2x. Fortunately, we have x, so we need to multiply and divide by 2. So we have half, that's outside the integration, and then we can apply the rule of sec squared, which is 10, and we keep the same angle, plus constant, option B. Again, integration of cotan this time. Recall that when you integrate cotan x, there is no differentiation rule that gives you cotan x, so there is no integration rule for cotan x. So you will try to use the log rule here. This is cotan, cosine over sine. So you will notice that the numerator is the derivative of the denominator. Derivative sine is cosine, so you have ln absolute value of the denominator plus some constant. So when you try to change the angle, if you make it like x squared, you need the derivative of the angle out there. So you need 2x, so that you can say it will be ln x squared. Exactly, here we have x, so again we multiply and divide by 2. So that's half ln sine x squared. So option D once again. Okay, so here we enter the definite integration area. And actually it's areas, that's where it all starts. So basically, as we explained before, as you all know, it all started with simple areas like rectangle and how to find this area, and it didn't take much to know that it has to be length times width. We have to multiply the dimensions to get the area of that. And then triangles come from rectangles, because any rectangle can be split into 2 triangles. So you can actually know that the area of rectangle is half times base times height if the area of the rectangle is base times height. Then follow other polygons. All other polygons follow from rectangles, because all polygons can be split into any number of triangles, so no problems happen. No problems. But then comes a circle. So what about a circle? So we have to do a different approach, and as we all know, that we could use the method of Archimedes, exhaustion method. So Archimedes suggested that we could exhaust or inscribe this circle between 2 polygons of the same side, the same number of sides. And as you increase the number of polygons, you increase your approximation. But at the end of the day, it's an approximation, and it was only all that we needed to do to actually find something like this. So if you have any curved area, then we have to think what would happen. But the same idea, and that's what Riemann has. That's what Riemann did when he introduced Riemann sums. So for Riemann sums, you have a planar region, and you try to split that region into as many rectangles as you can. And as you increase the number of rectangles, the accuracy increases, the error decreases. So that's George Riemann introduced the Riemann sums, which are the basics of definite integration. So that's the idea, the area of a plane region. You'll have a particular curve like the one that you see. You could try an underestimation and overestimation, take an average of that to get an approximation of the area. You could try to increase the number of rectangles to get an even better approximation. Okay. And then there are upper and lower sums. As you see, if you go below the curve or above the curve, again, that's another approximation like right and left sums. And you could get an average, you could increase the number of rectangles. So these are Riemann sums, actually. So they are sums. That's why we use the notation sigma for Riemann sums. Or Riemann sums use this notation because we're actually adding a number of rectangles, and each of these rectangles will have a width. Typically, we call it delta x, and the height would call that the function that we have, the curve that we have. So we typically say f of x, that's for length, and delta x for height, or call it length and width if you wish. Now you have number of rectangles. You don't have one rectangle, you split it into number of rectangles. So you put an index here, and you go you take as many rectangles as you want. Now, this is where we start to get from approximation to actual results. So limits. So if I can take the limit as this number of rectangle goes to infinity, then we actually have the exact area under the curve. So this is the great work of Riemann that really led to the fundamental theorem of calculus and definite integration. So this relation is very important to do any Riemann sums question. To know that a Riemann sum, to get the exact area, no approximation, the exact area, you need to take a limit. You need to take a limit of the sum of all rectangles. Okay, so in this case, if you look at delta x here, which will represent the width of the rectangle, it will be b minus a over n. Here a and b represent the limits or the boundaries of the area that you're trying to find its value. So it makes sense when you say b minus a, that's the entire width, and you partition it into n rectangles, whatever n you want. But then when you take n approaches infinity, so this delta x will approach 0. As n approaches infinity, that means that the width of each rectangle approaches 0, which means that there will be no gaps in the area. You'll have the exact area under the curve. So a classic Riemann sums question. So you have this even before we study, you ever study the fundamental theorem of calculus. When you see this notation, you know that stands for area. So we want the area or the sum of rectangles whose width is dx and length is given by the function x power 4. And we want that area between 3 and 5. So if we do some basic algebra, we can recall that x power 4 will look like this, something like this. And you're trying to find the area between 3 and 5. So this is the area that you're looking for. So you want to convert that to a Riemann sum. So let's get back to the last slide to remember what actually Riemann sums, what this formula actually gives you. It gives you a limit of the sum of the rectangles. So you need to specify your delta x, you need to specify your f of c or f of xi, as that is the length of each, or the height of each rectangle. So in this question, our delta x, again, will be b minus a, that's 5 minus 3, over n. So we will keep n. All the options have n. And then we'll take the limit as n goes to infinity. So that's 2 over n. So you have a limit of a sum, and that's the width of the rectangle, delta x, you'll just write 2 over n. So that's just the width. Now for the height, now we'll have to do a bit of work and look at the function that you have. So you have x power 4. So you know that you start at 3. You start as a 3 mark. So we're going to say 3 plus. So we start from 3 and we add the rectangles. We add how many rectangles? We add n rectangles. So here we have each rectangle that we add will have a width of 2 over n, right? So how many times do we add 2 over n? Yani if you look at this, this is the entire thing, or the entire width. And how many times? We'll call that k times or I times. Okay, so that's why we put a k here. And this becomes our index. K here goes from 1, from the first rectangle to the nth rectangle. And then we take the limit as this n approaches infinity. So of course we don't forget power 4, because this function is x to the power 4. So it's kind of like we start from 3 power 4 from this width, and then each time we add something to 3. The next one will be 3 plus 2 over n, then k equals 2, 3, 4, up to n, and n itself approaches infinity. So you will notice that this is option D. You could immediately have eliminated option A and option C, since the width of the rectangle is 1 over n, not 2 over n as we find. And then here you will notice that 2 over n shows up again, and when you add the width of every little rectangle that you have. Okay. Another classic Riemann sums example that you may have seen or seen something like it before. So you have some table and some function. This function actually is a derivative or a rate of a change. So as we read the question, it says a tank contains 50 liters of oil. So we got some tank that already contains some 50 liters of oil at time t equal 4. So that's when we start to record time, t equal 4 hours. So oil is being pumped into the tank at a rate r of t, where r of t is measured in liters per hour, t is measured in hours. Selected value of this rate are given in the table. Now we want you to use a right Riemann sum with 3 sub-intervals and data from the table to find the approximation of the number of liters at time t equals 15 hours. So that's after 12 hours. Sorry, from 4 to 15, that's after 11 hours. So you want the number of liters. So you already have a 50. And you're going to add something. You're going to add whatever happens in the next 11 hours. So what we can actually do to visualize this question is to draw a relation between r of t and t, since that's the data we have. So we start at t equal 4, say here, and if we take a rough guess here and say this is 6.5, so this point here represents the rate at t equal 4. Then if t equals 7, so say here's 7, it's 6.2. It will be a little below 6.2. Then at t equals 12, you will notice that here the sub-intervals are not exactly equal. And that's fine with the Riemann sums. They don't have to be the same width. They don't have to. So 12, 5.9. So that will be a bit below 5.9. Then 15, 5.6. So again, that's below. So that doesn't mean that we're decreasing. Actually, we're increasing the amount of oil. It's just happening at a decreasing rate, as you've studied in differentiation before. So here's the point. We have 3 sub-intervals from 4 to 7, from 7 to 12, from 12 to 15, and you want to use a right Riemann sums. So right, that means we will use the right endpoint of each interval to get the height of the rectangle. So this is what we're going to do. Again, for 12 is the right endpoint of the second sub-interval. So we'll do this again. and then 15 and do this. So basically you just want to find the area of 3 rectangles. So each of these rectangles will have a width and will have a height. So we got 3 rectangles. Be careful that each rectangle has its own width. The first rectangle 4 to 7, so that's 3. The second rectangle 7 to 12, that's 5. Then 12 to 15, that's 3 again. So when you look at the height, now we're taking the right endpoint. So we're interested at what the rate is at t equals 7. From the table, you'll know that 6.2. Then at t equals 12, that's 5.9. Then at t equals 15, that's 5.6. So can anyone do the calculation? Can use the calculator to tell me what's the answer to all that? Okay, so
114.9.
So 114.9, that's the correct answer. So you'll notice we didn't use 6.5 at all, and that's okay. I mean, you hate to leave some given not used, but this is the purpose of the question, to see if you know it's a right Riemann sum or a left Riemann sum. If it was a left Riemann sum, you would leave 5.6, you wouldn't use it, so that's fine. So on to definite integrals, and we said that it's Riemann who led us to definite integrals and the fundamental theorem of calculus. So this large expression, this limit of a sum, and all this notation can actually be replaced by the simple, as we said, elongated S. It's an S in the first place, but we just change how it looks because it's not a normal sum. It's a sum of an infinite number of pieces. So that's the definite integral. So an important relation that continuity implies integrability. All you need to know about a function is that it's continuous on a closed interval, to know that you can actually find the area under this curve, or to know that you actually can integrate this function. So a simple condition, a continuous function, that means it's integrable. Okay, so if we look at this question, it says determine the intervals in which this function f of x is integrable. So this is quite an easy function to graph. So if you graph this function, you get something like this, with that vertex being -2. Okay, so what do you think? Which intervals is it integrable? It says, is it 0 to 5? So this is 0 and this is 5. Of course, this line extends forever. And on the other direction. So from 0 to 5, it says integrable. So we can find the area between 0 and 5. Of course, we can find that area. No problem. Then there is another interval from -3 to 0. -3 to 0. So the question here, this sharp point at 2, does it mean that we can't integrate or find the area under the curve? And then at the end, -1 and 4. -1 and 4 will be away from the sharp point. So this is actually a trick question, because most students would like to say, okay, so 0 to 5 and 1 to 4, and negative 1 to 4. That's away from the sharp point. But in fact, this is a continuous function, and you can find the area under the curve for the entire number line. So even from negative 3 to 0, that's also an integrable. So that's the correct options for all intervals. Actually, for the entire number line, you can integrate this function. It's integrable because it's continuous in the first place. Okay, so the different integral, as we said, can be interpreted as the area of a region under curve. So specifically, if this function is continuous and non-negative, so if we guarantee that it's positive on this interval between a and b, now we know that the entire region will be above the x-axis. So we can say that the integral will be the area, which is always a positive quantity. We can't always say that it's the area, so that's why there's the expression, the signed area, because otherwise, if we have some curve that can be positive or negative for different intervals, say here and here, we're taking the integration between these numbers. Now we'll notice that we have up here an area that's greater than the area down there. So you'll get the net area. That's what you get. Assigned area, a net area. You don't get the area, the exact area between the curve and the x-axis. So it's very important to notice this. And this net area will be negative if the area below the x-axis were larger than the area above the x-axis. It would be 0 if they match each other. So to say that it is just the area, we have to make sure that's non-negative and continuous. This could easily be a question that you have in your exam. So it's important to understand this. Okay, so then the properties of definite integrals, the main properties of definite integrals. So if we integrate a function we start from a point and we get to the same point, we only get 0 because we didn't go anywhere. So for example, if we look at this sine function, we look at the sine x function. And we start from pi. We start from pi and we end to pi. So we didn't move right or left. So that means we definitely have no area. So this will be 0. So another property, if we have an integrable function on an interval, so the integral from b to a is negative the integral from a to b, so long that it's an integrable function. And then we have the property that we can split the integral from a to b via a point, any point inside this interval. So long that this function is integrable, so you can do this. And you need to do this in some context, like calculating displacement and velocity, where you need to know where the object has changed its direction, or when it has changed its direction. Okay. So, okay, the other properties is for even and odd functions. So again, we have an integrable function on a closed interval negative a to a. So if this function is even, the integral is double the integral from 0 to a. If this function is odd, the integral will be 0. So the classic example that we have here is for something like x power 2 and x power 3. So x power 2 is an even function. If I choose a number say -2 as the start of the interval and 2 at the end of the interval, you will know that the two areas will be the exact same. So the integral from -2 to 2 will be double the integral from 0 to 2, the same function. But for cubic function, you will know that if we go from -2 to 2, these areas will cancel each other, so it will always be 0. Okay, again, these are important conceptual questions, but they always come in exams. Okay, so this again, this is an odd function x, so it will get us 0. Even function will be the double from 0 to 3. Okay, so the other properties of different integral, we just discussed this sign and symmetry. So we have the fundamental theorem of calculus that we all know, that will have the antiderivative function, but just be careful that you need to subtract the values of that function b minus e, and be careful when you substitute and get the final value. Okay, so questions on motion now with integration. Okay, so this Zoom will end in about 2 minutes. When it ends, you will wait only 5 minutes and then come back to the same link. Okay, so if at time t the position of a body moving along the s-axis, whatever the s-axis is, and it could be the x-axis, whatever. that means motion along a straight line. So this is it, t power 3 minus 9t squared plus 24t. Okay, then the total distance traveled by the body from 0 to 3 seconds. Okay, so again, this is one of the most trickiest questions in motion, even though it's easy, because most students will be tempted to do this s of 3 minus s of 0. Now, this will only give you a displacement. It will not give you a distance. So this is why we need to find v of t. We need to know where the object might have changed its direction. So if the object changed its direction, then this means we have to split the integral at that point. So we differentiate this function, the position function, to get the velocity function. And we have 3t squared minus 18t plus 24. Take 3 as a common factor. Now you can factorize. So now when we equate the velocity function to 0, we get to instance where the velocity is 0. So it's important at this point to see what happens before and after these two instances. So it's easy actually to graph this velocity function as it's a quadratic. So we'll try to make a rough sketch. Of course, it will have only positive time. But the algebraic function will look like this. We have 2 and 4. So these are the roots of this function. And should be looking something like this. The midpoint here will be 3, of course, because it's quadratic. So here we are trying to find the total distance from t equals 0 to t equal 3. So we notice here that from 0 to 2, the object's velocity is positive, and from 2 to 3, the object's velocity is negative. So we'll need to do two integrals here. So first, we take from 0 to 2. Instead of taking from 0 to 3, on one go, we take from 0 to 2 the integral of the velocity function, which is 3t squared minus 18t plus 24 with respect to time. Plus, here we'll put an absolute value because we know that from 2 to 3, that integral will be negative, as you can see. So it will be negative, but we need the distance. So we have to take the absolute value of whatever comes from this. So it will be the same function. And here we don't have to integrate again because we already know how it will look like. We already know the answer of the integration. So we only needed to find the velocity to find that point 2 where the object changes its direction. So the integration will give us the displacement function t cubed minus 9t squared plus 24t. So here's from 0 to 2. We know this will be a positive quantity. And then we have the same function between 2 and 3. This will be a negative quantity, but when we take its absolute value, we'll get the distance. So when we sub t equal 3, what do we get? T equal 2, sorry, here. Here we get 2 power 3, which is 8, minus 9t squared, that's 36, plus 24t, that's 48. So we should say minus the function is of 0, but it will be 0 because we have t involved here in all terms. So we can proceed to the next part, which is when you put t equal 3. So again, don't forget the absolute value here. So when we put t equal 3, you get 27 t cubed minus 9t squared, that will be 81. We're subbing t equal 3 plus 24t, that's 72. Minus, when you put t equal 2, you'll get the same thing you got here. So if you work that out, it will be, I think it will be 20. 8 plus 48, that's 56. So this is 20. So we'll get 20 as well. So when we work, so the first part is 20. Let's continue up here. So this part here is 20 plus absolute value of this part. We have 72 plus 27, that's 99, minus what? Minus 101. So that's negative 2. So you get 22 option. If you would calculate this v of t from 0 to 3 on one go, you would get 18, which would be a wrong answer. So it was important to find these 2 points. Okay, so that leads us to another application of definite integrals, where it can help find the average value of any function. Well, most commonly, you're asked to get the average velocity, average velocity. So use the same thing, use the same formula. You integrate the velocity and you divide that on the width of the interval. So this formula gives you the average value of any function. So say that your function has lots of ups and downs, and you're looking at some interval, say from here to here, 1 to 5, for example. we're not looking at the area anymore. We're just looking at the curve, at this curve from 1 to 5. We're looking at this portion of the curve. What is the average value of the function? Here, near 5, it has higher values. Here near, say near 3, it has lower value, and then it has negative values near 1. So the function is changing all the time. What's the average value of this function? Exactly what you get when you do the definite integral from a to b. Say here from 1 to 5. This is called f of x. So you integrate f of x from 1 to 5, and you divide by the width of this interval, which is 5 minus 1, which is 4. Okay. So this is the average value of a function. Okay, so here's another question on the average value. It says you have a continuous function from -4 to 4, and we want to know what is the average value of the function on this interval. So if we use the same formula, we'll say the integral of f of x dx from -4 to 4 over the width of the interval, which is 4 minus -4. So we know that we have 8 down there. That's the entire length of the interval. But we have a problem that we don't know what the function looks like. Actually, it looks like a piecewise function, but we have a different 5-line segments. Now here we will use our understanding of definite integrals. So exactly what this means. It means, as we said before, this will be the net area, the net signed area. Could be positive or negative. So even though we don't know how the function looks like, but we can find the area, we can find this area. But notice that we'll have a positive area above the x-axis, and we'll have negative area below the x-axis. So we have to get the net area. That's what we have. That's the value of the integral. So if we look, actually, since you have square units here, all these squares on the grid, you notice that this area is 1. You have 2 triangles that add up to 1 square. So, or if you use the formula for a triangle, so you have half times base times height. So for the first triangle, the area will be half times. Okay, let's write it here. Half times the base will be 2 units, and the height is 1. So that's just 1 as we expected. So the second area, the red area, it will be negative. So we'll put a negative and calculate the area. We know it will be a negative. So the width here is 3 from -2 to 1. So we have half times base, which is 3, and the height is 2 from 0 down to -2. Okay, so then we have a positive area. The purple area is positive. Can split it into triangle and the trapezoid. So this triangle will have an area of half times a base of 2 times a height of 2 as well. And the last trapezoid, it's clear, 3 over 2, 1.5, 1.5 square, and you can calculate. So what we get here is 1. This is 1, and this is -3, and this is 2, and this is 1.5. So you can notice here that -3 cancels with +3. These would cancel, so you'll have 1.5 up there, 3 over 2. 3 over 2 over 8, so that's 3 over 60. So that's the average value. So if you look at the graph, where will 3 over 16 look like? It looks close to 1/4. It's not 1/4, but close to 1/4. So if you look at this point, let's make it a special point. If you look at this orange point, quarter the distance between 0 and 1, that's the average value of the function. And that makes sense because when you look here, you're going up and you're positive here, and then you go negative, and then you go positive again. So it's like a mean, like if you have the value of the function at every single point in this interval from -4 and 4, and find the average of all these points, you will get 3 over 16. So on to differential equations, which is, we can say, another application of integration or closely related with integration. So again, the definition of differential equation is simply an equation in x and y. Okay, so it involves x and y and derivatives of y. So that means we have a rate of change, we have a derivative. And to solve the equation, we need to find the y, the function itself. So y, that's what we call a solution or a solution curve. And we will have, as you know, a family of curves, a general solution that can be reduced to a particular solution given some initial conditions. So to call a function a solution, it needs to satisfy this equation. So it satisfies the equation when y and its derivatives are replaced by f of x and its derivative. And this is a type of question that always happen. He could give you a differential equation. This one is not very hard, but you could get something very hard, and you're required to separate the variables, but you can't separate the variables and you can't solve, but you're given a solution and you're asked whether the solution is actually satisfies. So all you need to do is differentiate, get y dash here, as you know, be -2 e power -x, and then replace y and its derivative, okay, by f of x. So what's f of x? This is f of x, اللي هي e power -2x. Okay, what's y dash? -2 e power 2x. Does it satisfy the equation? Yes, satisfies the equation. You have -2. So this is a solution. This is verified as a solution of the differential equation, and we talked about the order and the degree. So the typical question that you almost know that you'll have to answer this question in the exam, this type of question about the growth function. So dy dt equals ky. So the rate of change of y with respect to time is proportional to y itself. And the proportionality constant is called k. So here in the table you have two initial conditions. These two initial conditions will help you get the constants. And since you're given two conditions, you expect to have two constants in your solution. So typically this is what we do with this kind of question. We divide by y here, both sides, and we divide by y and multiply by dt. So you get this, and we all know how this ends up, but we can do it. So here we have ln y, on the other side we have kt plus, we'll call it c naught, like, because we're gonna have another constant later. So we exponentiate at this point. We raise both sides to the base e, and again we can separate these because when you have two numbers are added in the power, that means that you can distribute it on the base. So we all know it will look like this. The whole point of exponentiating is that E and len, they cancel each other, and you're left with y here. And then with a bit more work, you could say that y is positive or negative e power c naught, e power kt, and then replace this entire thing with another constant, since it's a constant at the end of the day. So we're going to assume that this constant is another constant called c, for example. So this is our solution, y equals c e power kt. As we expected, we have two constants, k and c. So if we use the first initial condition at t equal 0, y equals 4, so 4 equals c e power 0. That means that c equals 4, and we can write the equation 4e power kt. To find the second constant, we do the same, sub t equals 2, so 4e power 2k equals y equals 12. So this means that we can just simplify, and we have e power 2k equals 3. And here to get the k, we can take the len for both sides again. Len will cancel the e, and we have 2k equals len 3, meaning that k equals len 3 over 2. Okay, if we put all this information back to our equation, so y will be 4e power k, which is len 3 over 2, and we have t, so that's option B. And you can know for sure that this kind of equation always ends up in this form. You don't have to solve it. You know, it will look like this, and you notice that all the other options, they don't look like this, but you could have the same form in all options with different changes. So you need to keep in mind that you need to find the constants. Okay, so another question. We'll have a couple of good questions now on differential equation. This one is not very hard, but we'll go through it. The population of a city increases continuously at a rate proportional to the population. So this means we have the same type of differential equation, dp dt proportional. This is how we write it, with p, and then we replace this by a proportionality constant. Typically we call it k, so kp. We don't need to do the same thing again. We know that this will end up like this. We have p equals c e power kt. We just did this in the previous example. This type of equation always has this general solution. Now here we start to work, because we use this initial condition. The population doubles in 50 years. And then the question is, after 75 years, what is the ratio between the population to the initial population P naught? So the initial population P naught, this means that at t equals 0, the population equals P naught. This is the initial. This is actually an initial condition. And then we have another initial condition, that at t equals 50 years, the population is double the initial, 2 P naught. So we use this information to find the arbitrary constants c and k. So if we use the first condition, t equals 0, you will have c equals p naught. We replace p with p naught, and t with 0, e power 0 is 1. So we know now that this equation looks like this: p equals p naught e power kt. Okay, so we use the other condition as well. T equals 50, p equals 2 p naught. So we have p naught e power 50k equals, instead of p, we write 2 p naught. 2 p naught. Here you notice that P naught cancels from both sides, and you're interested in K, so you have 2 equals e power 50k. Again, what we do here, we take len both sides, so len cancels e, so we know that 50k equals len 2 and k equals len 2 over 50. Now we can sub that back into our differential equation, and we have b equals p naught e power, instead of k we write len 2 over 50, and we have t, don't forget. So this is the particular solution that we will use to substitute after 75 years. After 75 years, so at t equals 75, p will equals p naught e power 75 len 2 over 50. What we need is the ratio between this population after 75 years and the initial population. So we need to divide this. We need the ratio between B, between this population at t equals 75. We need the ratio between this and the initial. So we divide by P naught, which cancels. And now we're left with e power len 2. We can write it this way, power 75 over 50. Because you know that when we multiply the two powers together, we get back the same power. So we write it this way so that we can cancel e with len. So what we have is 2 power 75 over 50, which cancels to 3 over 2. So what's 2 power 3 over 2? So that's the square root of 2 power 3, this, which is the square root of 8, which is 2 root 2. Of course, over 1, because we're looking for a ratio. So that's option D. Okay. So slope fields are just a graphical tool that we use when we can't separate variables, we can't find the solution to the differential equation, we look to slope fields. So this is a typical question that you have with slope fields. So what you're looking for is you look for patterns throughout the graphs. The most basic pattern is horizontal lines. Whenever you see horizontal lines, that means that the slope is 0, and the slope is actually what the differential equation gives you. So here, if you look, x plus y equal dy dx. When you look at x plus y, I'm looking where x plus y equals 0, because I'm looking for horizontal segments. Horizontal segments mean that the slope or dy dx is 0. So this will mean that y equals negative x. So we draw the line y equals negative x. Try to draw that on all the graphs that you have and see which one has horizontal lines. So you'll notice it's graph B. It's B. Here, at all the points on this line, you will see that you have horizontal segments. So that's this is a slope field of our differential equation. Okay, so this is a good question. At any point of intersection of a solution curve of the differential equation, dy dx equals x plus y, and the line x plus y equals 0. The function y at that point is equal to 0 or a local maximum or a minimum or has a point of inflection or a discontinuity. So if you look again, intersection of two things, intersection of the solution curve, of a solution curve, and this happens to be the same differential equation that we had in the previous slides, x plus y. So now you know that how it looks like. It looks like B. You don't have to know, but now you know that it looks like option B. So when we say a solution curve, so this is a particular solution, a particular curve, because the slope field, you can see a family of solution. For example, a solution curve will look something like this. Another solution curve, if we choose any arbitrary point as a starting point and go between the lines, it will look something like this. So suppose that we have a solution curve and you're asked about the intersection of this solution curve with the line x plus y equals 0, which is y equals negative x. So what you're asked about is what is this intersection will be. So it looks like it will be one of those horizontal segments, because those horizontal segments, they lie on the line y equals negative x or x plus y equals 0. And at the same time, they will lie on a solution curve, because any solution curve will have to pass through one of those points. So that means something. That means that this point will be either a maximum or a minimum. But the question hasn't been too easy to just include a maximum, so you have to do more work to know if it's a maximum or a minimum. So here it will be a minimum, because you need to do a simple sketch. So this is our y equal x, sorry, our y equals negative x. We can actually use the previous slide. So we'll draw again y equals negative x. Just a second. Okay. So this is the line that we were interested in. So at all these points, we have horizontal tangents. Okay, we have horizontal lines. So suppose I've taken a point like negative 2 and 2, this point, negative 2 and 2. I'm going to take a point to the right and another point to the left and substitute in my differential equation and see what happens. So if we have a negative slope to the left, then a positive slope to the right, then this means this point is a minimum. If we have a positive slope to the left and the negative slope to the right, it means we have a maximum. So this means we don't have to see the slope field. We just need to substitute. Pick any point like negative 2 and 2, since it satisfies the equation of the line you're given, x plus y equals 0. Now, if you pick a point to the right, so you change the x, negative 2, you could be negative 1. You can keep the y, negative 1 and 2. So at this point, what happens? When you substitute negative 1 and 2, you get a positive value. So that means the slope is positive after. If you take a point to the left, like negative 3 and 2, and you substitute negative 3 and 2, you will get negative 1. You get a negative slope. It means that you have been decreasing before and increasing after, so it's a minimum. So this point is a local minimum. The intersection point will be a local minimum. Okay, so a function f of x that satisfies the equations f of x times f dash of x equals x and f of 0 equals 1, which of these? So this is another way. This is a differential equation written in another way. So always you need to just simplify. Use y instead of f of x. Y dash instead of f dash of x. or better dy dx equals x. So now you'll need to separate the variables. So I have y dy, and if you multiply by dx, you have x dx on the other side. And then you'll integrate both sides. Here you get y squared over 2. Here you get x squared over 2 plus some constant. Again, we'll call it C0 because C0 because often we get new constants that don't really matter. It doesn't matter if if we multiply this by 2, the entire equation, it will look like this. It will be plus 2C0, but again, a constant multiplied by 2 is just another constant, whatever it is. So we're going to call it C, new constant. But that makes the equation a lot easier to work with. We got rid of the 2. So you need a solution, you need the y. So y equals positive or negative square root of x squared plus c. Now, which of these options might be a solution? So it looks like the first one. If we have the constant equals 1 and we're taking the positive root. So that's the only option. That's the only thing that you could get from the options that matches our family of functions.